Hello, everyone. Thank you for coming here. I hope this is going to be interesting. I could go on and talking for many, many hours because there are so many interesting things. So we'll have to skim through a bit some of the concepts. Some might be a bit overwhelming. Sorry for that because it's all very new ideas coming together. So quick introduction. Well, I'm Sanne Grinovero. I live 20 minutes walking from this place, but I'm Dutch and Italian. So it was interesting to submit here. I work at Red Hat in the middleware area. I'm best known to lead now the Hibernate team, but I've been having some fun with the engineering on Quarkus. And well, it's funny to see Heinz here in first line because we started this pretty much at JCrete after having some conversations there with some people from the Oracle GraalVM team. It was like an interesting challenge. Like, would it be possible to run these other things like on GraalVM, considering those limitations I was hearing for? And so that was a challenge, and that's fun to take. So today I've been, well, recently, or in the few years, I've been contributing to several other projects. Most notably Hibernate, but there is a larger list. So we're going to talk a bit about GraalVM and what these native images are that I keep mentioning, and then like what's Quarkus and how it plays and integrates with these things. I'm going to show you what these live coding aspects of Quarkus are, and I try to squeeze in a bit of background, like technical, how this is working and how this is pulling this magic together. So native image, what is it? It's first off, it's a tool that you download. So if you download the GraalVM distribution, it comes with a tool called native image that's able to convert a Java application into a native binary. So that's a platform-specific executable, which can run without having a JVM installed on your target. So once you download it, it also has a Java distribution. So there is a JDK there. At this point, it's Java 8, but Java 11 is coming soon. So you download and unpack it, and then to use Quarkus at least, you need to point both your GraalVM environment variable to this distribution and your Java home distribution. You probably want to have it on your path as well so that you can invoke these tools. And then, well, it doesn't matter how you build your application, but first you have to create your jar. So let's say Maven package in case you're using Maven. And then there is this native image tool that can convert it and run it as a binary. Now, to make it clearer, I'll just do it right away. Right? So we have here, a very empty project with a hello world file. Right? Everybody knows how this looks like, and now we're going to compile this as a Java application. So now we have a class there, and now I'm going to create an executable jar out of this. So let's see if I get this right. I want an app jar. This is the main, and the main class needs to be included. So what we have now, we have an app jar, and I can run this, like this, hello world, easy. Now the next step is really just running native image and saying, I want to convert a jar, and it's the app jar. Now, this is starting a JVM in which the GraalVM compiler is running, and it's analyzing this jar very thoroughly, and it's also analyzing all its dependencies, like in this case, the JDK. So it's not that small, this application. Like there are many models from the JVM, from the JDK being compiled as well. And there are some more components from Substrate VM, which are replacing some components in the JVM, which make it possible to output this little binary here. So this is a 2.4 megabyte file. This is a Linux-specific, platform-dependent application. So it's linking, directly, and you can run it as a Linux application, right? Now, you can drop this into a Docker image or like an application to run somewhere else. It does not need the JVM. So this is a 2.4 megabytes. In this case, it's dynamically linked to some other library, so you will need a thin Linux distribution around it to launch it, but you can also create like statically linked libraries. It will become slightly larger, but then you can like create a Docker image, which is just containing the executable. So that's what the native image is. And we think that was like super interesting, like in terms of potential of where you can bring, Java written code into different areas that we have not like traditionally used Java for. So the question is, like, what about more complex applications? And the problem is there are several limitations in what code can be compiled to native. So since one of the strongest points of the Java ecosystem is like this very rich environment of libraries, it turns out that most of these libraries are using things that are like a violation of the expectations of the GraalVM compiler. So you cannot just take any dependency and compile your whole application and still create a binary. That's very complex. There are lots of flags and very interesting things that you can do to get it working. So it's not that it's not possible, but it's a lot of work, and it's you need to learn several new things. So let's learn some of those things. So what is GraalVM? Well, it's this name. It contains several components, right? So like you've probably seen some of the other presentations here about it. I'm not going to talk about truffle and Sulong and how this is very interesting to run, additional languages, mixed languages, or, as a toolkit to create your own languages and so on. What we're talking about here is the GraalVM compiler. I mean, these are the components that we're using. GraalVM compiler is able then to compile, bytecode into highly optimized native code, and the substrate VM, which is one of these components here that's replacing these platform-specific bits of the JDK, let's say. So what you're doing when you're doing this ahead-of-time compilation is you're combining your application classes, the JDK classes that you're using, and some substrate VM classes, again, only the ones that you're using. And there you get your executable, statically or dynamically linked, that doesn't matter. Now, the compiler itself is really advanced, very modern. It can do lots of very clever things. Now, what I like a lot of it is its capability of really pruning out from the executable anything, like any symbol, any method, any constant that your application is not going to need at runtime. So, example, Hibernate. It has support for a ton of different databases, and among of these you have the Oracle database. If you try to create a leaner version of the Hibernate jar, which does not support the Oracle database, you quickly find out yourself patching about 600 classes and removing 280 out of them. Now, it turns out in Graal, if we can prove to the compiler that we're not using Oracle, but we're using Postgres, all of that code gets physically stripped out of the binary. So it's not there. And this enables more optimizations, like more code inlining, more constant folding, and many interesting things. Now, to do this, of course, it needs to run a complete static analysis of your executable. So you need to tell the compiler what's your entry point, which potential other entry points you're having if you're building like a binary, like a native library. That's also an option. And of course, this is based on the assumption that all the code that you're feeding to the compiler is all the code. You're not going to load anything dynamically later, because that's, how can it remove safely all these other components that it has proven that you're not using if then suddenly, a new class materializes which might be needing some of these modules that you actually stripped out from the binary. So these are limitations, but they're also like its strong point, right? The fact that it can do this very advanced proof and remove all the things that you're not needing are a great thing in certain environments, in certain contexts, right? So it's a drawback, but it's its strong point at the same time. So the idea is we can actually embrace that, but let's see some more of these limitations. So dynamic class loading, as I said, is completely out of the question. Like, you cannot have a reference to a class loader. You cannot load anything dynamically at runtime, which is a big deal. Like, there is pretty much 0 frameworks out there that can work when getting a reference to a class loader returns null from the platform. You'll get null pointer exceptions guaranteed everywhere. Because we have been developing things for years with the assumption that certain APIs are working in a certain way, and that's not really the case in this platform. So you can't really blame the original developer to not have checked for null for these kind of odd situations. So there are implications here, like it means, like, well, there is a typo there, deploying anything like in a container is out of the question, which means like having a Tomcat or an application server, anything, and the idea that you have words that you deploy into it dynamically, or plugins in your application that then get loaded, that's not something that can be implemented here. Well, it can be implemented, but you need to deal with it in terms of native code being loading other native code, not in the traditional Java container way. So is this a big problem? Well, maybe not really, because nowadays we're designing things which are supposed to have like a single runtime, a single container per service. So you're building this single service for cloud-native applications or microservices. You don't really expect to mutate the code that's running in that specific container. You would rather spin up a new version of the container or new copies of the container or new flavors of this application. So it would be like a different build configuration, but not particularly a problem anymore with current ways of developing. There are several other limitations which are a bit more nastier. So like the tool interface, the management beans, which means like no agents. So you can't use JRebel, you can't use Byteman, profilers or tracers in native mode out of the box. Now there actually are some flags that you can make sure that during the compilation phase, some levels of tracing and some tools have like a backdoor, but you have to opt in advance for some of these. Because, of course, JRebel and Byteman, for example, they would try to mutate code. There is no bytecode. There is no compilation. So that's just not possible. And, of course, it would violate this principle of closed world that the compiler has been seeing all the possible code up front. Well, the no Java debugger is annoying. But, you can always run this in JVM, debug it, and when you know it's great, you compile it to native. And of course, it is a native binary, so you can still debug it as well as a native binary, right? So GDB and so on. Now, there are more consequences here, like there is no security manager. And again, okay, if you are not allowed to load any code dynamically, maybe that's not a big issue either, right? The main problem here is that many libraries we have are meant to run on the JVM as well. So there is code in there which is dealing with the security manager, and that code will not compile. So you need to find a way to have a flavor of your library which doesn't use the security manager, or for which the compiler can see that that code is entirely dead and there is no way to reach that code. And then it's fine. Save for like a finalize, which is actually great because it's been deprecated since a long time. We're all working to try to get rid of these finalizers. Turns out if you compile a large complex application and you think you got rid of all your finalizers, the compiler will spot some. And so that's a compilation failure over there. You're doing something which is entirely legal on the platform. So you're motivated to go and fix it right away. This is sad news. Like invoke dynamic and method handles are having very limited support. There is some support, and this might improve. I don't know. This is, the problem here is this is almost like dynamic coding. You can do very complex additional things with this. But the good news here is that as far as the needs for Lambda implementations, these are working fine. So you can use Lambdas. You cannot use invoke dynamic and method handles for more complex things. Reflection. Well, reflection gets very much into the territory of confusing the compiler of what you might possibly do at runtime. So it is not allowed, with the exception of, if you tell it up front. If you say to the compiler that you might be invoking that field, or you might, need to change that final field, which is otherwise a constant, but in the JVM, normally we cannot really rely on that being a constant all the way, right? Because there is a reflection, you might break it. So here, the important point is more like you need to make a thorough list of all your reflection needs of your application and all your libraries, so that the compiler can keep those in mind. And the same is for dynamic proxies, not allowed. And loading resources only if you told him upfront, and using JNI, unsafe memory, etc. Now, static initialization is another very interesting point, and this actually just changed it in GraalVM. But the idea is that all your static initializers are run during the build, not at runtime. So you might look at constants in your code, like we're all used to see constants like public, static, final, string, something. Now it reads as a constant for us, but in terms of JVM initialization, we know that that code is actually being run when that class is first initialized. And some frameworks rely on this kind of behavior, like because we're used to it, and you can do some interesting tricks with that. It doesn't have to be just strings, and it's not really a constant either, right? Normally, now GraalVM actually runs this during the build phase. So, for example, if you are setting along to the current timestamp, and then try to read this number, you're not getting the number of when it's being run, but when this application was compiled. And now, there are some cases in which this is not done at build time, because if it's starting threads in a static initializer, lots of frameworks do it. Like it's a bad idea, it's a bad pattern, but especially if you take a large application and start to try compiling it to GraalVM, you will find, oh, this library is doing that, that is doing it as well, and everybody has like some good reason to ask for an exception and say, well, this is a special case, I need to start my thread here. And same for opening files and opening sockets. These operations are not allowed in a static initializer because, of course, you are compiling the application. So it would really feel odd if when you're compiling your thing, suddenly in background, the compiler is trying to connect to your production database and do some stuff. So it's a good idea that these things are like a violation in terms of like the GraalVM will report this as a violation. Or you can defer these things to be actually run at runtime. And I think that's what just changes. Like the default now is to detect if you're doing something illegal. If it's illegal, it will be deferred to runtime. If it's safe, it will be run during the compilation phase. Now, what happens with these constants? They are in the heap, and the compiler takes a snapshot of these things, and these are constants. And those objects get copied right away into the binary. So they don't have to be initialized again when the application is actually starting, and it gives you, an additional boost. And then, it knows if you can ever mutate any of those. So it also knows when you will never mutate them, which means these are, again, constants that the compiler can rely on to make some more optimizations. I talked ahead about this, we said this. So a quick example, like how do I disable a feature? For example, in Hibernate, there is a configuration option to say, like, do you want me to register statistics in the management bean, right? So you might want to set that in the configuration file. Now, the problem with GraalVM is it's not really enough to make sure that you have it off in your configuration file, because the compiler needs to prove that you will never, ever enter this method, no matter what the configuration is going to be at runtime. So the only way to persuade the compiler that this code is safe, even if the register JMX method here is invoking something on the management bean, is to have code like this. Right, this has to be a constant. You cannot have a real constant, right? So you cannot have any reflective code which enables it to like bypass the fact and maybe dynamically enable this branch. So the compiler needs to be able to see that this whole thing is safe to be deleted, and the constant is safe to be deleted as well, and all the code can completely go and be removed from your output. So you can think, I just need some tweaks on your code, but the main problem is that all your dependencies need to be included as well. So any library and any dependencies of all of your libraries need to be made compatible with GraalVM. And that's sometimes a ton of dependencies, so that's a lot of work. And let's have like an idea of what the impact was on Hibernate ORM to make Hibernate compatible. I have a mind map. I won't scare you by reading all of this, but we can browse through it quickly. And some problems are very simple. So, for example, resource loading. Hibernate has a configuration option to have you import a SQL statement when it's first run, like initialize your test with some seed data. So what we do is very simple. During the build, we see, do you have that configuration option enabled, and do you have such a script? If it's there, it's being registered to be loaded into the binary as a resource that's available at runtime. If it's not there, we will not register it, and so on. Pretty easy. Now, for management beans and security, these are simply disabled. There is no need for that in this platform. And then, of course, we have to patch a lot of things. For example, I discovered that the background, there is the default thread pool has like a management thread, which has like monitoring things on how the state of the connections are. And this is being initialized very eagerly. We don't want that. So, you have to patch some libraries in this case. And then, of course, reflection. Hibernate is known to be one of the biggest users of reflection. Now, it turns out, in reality, it doesn't really use reflection at all, if you enable the right flags. Right? We have several other alternatives to access your fields or read your things, and some of these are by bytecode enhancing your entities so that we get like direct field access to these elements. Now, the problem with that is, well, within GraalVM, we cannot change your bytecode, so we cannot do that. But we also have tools that allow you to do the enhancement of entities at build time. So to get this running on GraalVM, all you need to do is make sure, for this specific problem, each problem here is a different solution, but for this one, what you need to do is make sure that you have these build tools enabled so that your classes, after being compiled, are enhanced with the Hibernate tools so that they get modified, and then that makes it possible to use Hibernate without having to modify your code dynamically at runtime, which has more benefits as well. Like we usually recommend this, but people are lazy. They don't want to set up an additional build step phase. So we have this fallback idea, which is, okay, well, let's go for a reflection at runtime or proxying at runtime and so on. Now, I mentioned dependencies. So this has been a bit of work. I have been patching the PostgreSQL driver, the MariaDB driver, the Microsoft SQL driver, the H2 driver, and we're working on some more drivers. But you need, each of these had some stuff which isn't entirely working. And so, for example, the Postgres driver, I managed to push all my contributions to the community, and they were accepted. So this will just work on GraalVM out of the box. You don't need Quarkus or anything of this. The other ones here are needing some of the magic that Quarkus adds on top to still, be compatible with the platform. And then, of course, there are many other frameworks and libraries. But let's go to metadata and annotations. So another thing that Hibernate needs to do is figure out what's your model, where are your entities. Normally this is done by class path scanning. Let me find all the objects which are annotated with like JPA-specific annotations. And then I want to read all of their properties via reflection. So like, is there a public constructor, which getters you have, what's the ID, and all these things we need to know. Now the trick here is simply, don't do it at runtime. Since your code cannot change, we can do all of these things at build time. Like normally we have to do it at runtime because half of your stuff might be dynamically generated or hiding in something which, then magically new entities appear or something. But since we're living in a world in which we have this assumption of closed world and everything is known during the build, then we can take advantage of that. So in the Quarkus build, we are plugging into the build lifecycle of either Maven or Gradle. And there is a phase there in which we analyze the whole application very efficiently by using Jandex. It's mentioned here. So Jandex is able to get metadata out of the structure of the whole class path without actually needing to initialize all these classes. Like initializing all those classes would be slow, and we want to be fast here. So from there, we get an immediate index of like all the entities which are available, how they are mapped, and all these things. And then what do we do? Now, the funny part is, where do we store this data? We're running during the build phase, right? What we do next is we actually start Hibernate within the compiler's JVM, right? And we'll see what that benefits. And then the half-started Hibernate, like we cannot connect to the database because you're compiling, right? But we can start everything and verify all the validity of your model and actually build our internal models and all our internal data structures. And then these get snapshotted and they become a constant for the compiler. So you can get more benefits out of that. For example, let's say we see that in your ID generations, you're never using the UUID strategy to generate IDs. That means that all the code that we have to generate UUIDs for IDs can be removed as well, right? Because all of this stuff, which is normally highly dynamic, happening during the boot, and that's what taking a long time to start an application in a server, can be done during the compilation phase, certainly. Now, the same principles apply to like proxies and bytecode enhancement and etc. So all of these things are done during the build phase. There are other interesting aspects here, like the configuration parsing. Typically, this is an XML file, with Hibernate at least, the persistence XML in metainf. Now, what we discovered, was trying to analyze why does it take so long to do like a cold boot, like a cold JVM, which is booting right now, to get to the point that the whole Hibernate application is started. And you have this single point in which you're parsing one configuration file, which is an XML file. And that's the only time you ever use XML files, maybe in your code. Now, it turns out that parsing an XML file is quite cheap because the XML parsers in the JVM are pretty good. But first, you need to initialize the modules that can do parsing of XML files. And there is a cost of metadata attached to all those classes, which I measure to be around 19 megabytes of memory. Right? So if you take a JVM and you start Hibernate and you have to quickly just parse one configuration file, which is an XML, you're consuming 19 megabytes of memory, which you never can get returned later, because that's metadata of the class definitions. And so let's get quite big. So this is like an overview of all the things we had to do specifically for Hibernate. But it's all like a series of techniques and ideas that we evolved. And the idea here of this talk is that Hibernate is one of the most complex frameworks, as far as I know, in terms of stuff that it's doing, quite low level with like bytecode enhancement and all those things, or class path scanning, and So after we have done this one, it means like all the other frameworks are a bit like a downhill, right? They're going to just have like a subset of the issues we had in this case. So let's go on. So what is Quarkus here and how does it fit? Well, we define it on the website as a toolkit and framework. You can also see it a bit as like an extension of the build tool, or something that's closely interacting with the Graal SDK to make sure that when the GraalVM compiles, it can actually have some callbacks into code which is specific for each framework and possibly different, to dynamically make adjustments to the needs of the compilation phase. Oh yeah, and supporting Kotlin as well. So yeah, it's really designed for clouds. So the idea is the application is not changing. We know that. We can take advantage of that. And these limitations that GraalVM showed us, initially they scared me, and after toying with that and embracing them, you can see that they are actually strong points for what we need to do in certain cases, right? So the flow here is you compile your application, and during the compilation phase, there is a Quarkus plugin. There is one for Maven, one for Gradle. We could create some more. This is manipulating your application. So it's analyzing your code. For example, like I mentioned, I need to know who all your entities are and so on. But then it's also modifying your code. So you don't need to set up these additional build enhancers that you would have to set up separately, because we can run all of that in a single phase. And that gives us a bit of speed in execution. Now, what you get out of there is a highly optimized jar application, which can run really well, both on GraalVM native images, but also on HotSpot. And actually, it's surprisingly great on HotSpot because, well, of course, you get really good performance in this scenario. It's maybe best for larger applications and maybe on the right side, you do it for smaller things, for which like size of memory is your important point. But even there, the savings in memory of having avoided so much work at runtime are really strong. So these extensions, we have now a large collection of extensions. you can see them as components that integrate closely from one side with the Quarkus build lifecycle and the other side with the specific library and framework. So for example, there is the CDI one, which does dependency injection. It will analyze all your code, see all your injection points, producers, and everything, and then all the code that's needed to wire these dependencies together is being generated at build time. It's a bit like a Dagger, if you remember that. But the critical aspect here is that all extensions are applied in a single phase of your application. So there is one phase of analyze of the application and one phase of class loading in which all the bytecode is modified at once. So this is a bit of an idea of relevant frameworks that we're supporting today. Well, Vertex is there, lots of fun with reactive there. Well, we have REST Easy. CDI is not on the list, but it's there too. And Apache Camel, which comes with a huge list of integrations. Netty is supported. We have the Infinispan client to connect to data grids remotely, the Kafka client, Prometheus, Jaeger, and a lot of integration with Kubernetes. Now, one aspect of the platform aspect of Quarkus is that it's also a bit of a runtime. So since we can do all this magic during the build and have a whole notion of what you have and how to enhance these classes, we can actually enhance many other things. So we expose some new APIs, and the APIs we're exposing, we try to have them both in imperative option and a reactive option. So if you are more in preferring one side or the other, you have choice there. It's meant for containers. So these outputs are very small size on disk, and I'm not talking just about native image, right? Even the traditional JVM target is much smaller than what you would see on a different framework, because there is this split between runtime needs and compilation needs. So there are lots of dependencies that you might need during the deployment and augmentation phases, but you don't actually need at runtime. So for example, I said Hibernate gets configured via an XML file, which is parsed only once during the build. This means that technically you don't need an XML parser implementation in your runtime, right? So if you take advantage of Jigsaw and the modular environments, you could technically remove the XML parser from that output, unless you're needing an XML parser for other reasons, of course. So fast boot times are really important now for clouds because it allows you to scale up dynamically depending on load. You don't have to, pre-warm images many minutes in advance. And we're looking at resident set memory rather than just heap size. That's also important in containers because if you are breaching the amount of total memory that your application is using, cloud containers like Kubernetes will kill your application. So you need to keep in mind what's the total memory of your application, not just a heap, which is a component that we're looking at. As Java developers, we look at the heap because that's where our mistakes are visible, or that's what we can work on. But when you're running in a cloud, you need to keep in mind that every thread that you're starting needs its own stack, and every class you're loading has a bit of native memory used by the JVM. And so when you're dimensioning, like how much memory will I need for this container, you need to take into account these additional things, and that's what we're doing here. So this is a memory to measure resident set. That's how we do it. So let's see some numbers. So if I run a simple REST Easy application, the best, so this is a demo using REST Easy and Undertow for the web. On other stacks, which I won't name, this will take you at least 140 megabytes of resident set. Right? This is not just looking at heap, this is looking total cost of what your container is going to need. If you run the same on HotSpot via Quarkus, it's a little bit more than half of that size. That's just the savings of not initializing all the stuff that you're actually not really needing at runtime. And of course, you have the option of compiling into a native. In that case, you need 13 megabytes total memory for your application. So when you're paying, a single instance on, say, Amazon, you can see that the cost is really memory. So, this means that pretty much your cost in terms of billing on Amazon is just 10% of what you're paying on an alternative platform if you compile to native. Or if you prefer using HotSpot for performance reason, it's still just half the cost, which is a pretty good saving there. Now, if we throw in JPA as well, there are many more components being run. So you have Hibernate, but also you have like a connection pool, the GDBC driver, a transaction manager, a caching library, and I'm probably forgetting some more. Now, in that case, traditional other stacks will be at least 280, with Quarkus running on JVM 130 and 35 megabytes. But let's see bootstrap times. So we're not we're measuring the time from not having started the application to actually responding a first request. That's important because some other servers cheat a bit, like the report, I'm up, then the first request comes in, and then, oh, I need to lazily initialize some other components, and so that first request might take a bit of time. So we measure time to first request. Well, running in native, again, just the REST thing will take about 14 milliseconds from not having started to responding to your code. On HotSpot, still less than a second. With other technologies, we are beyond 4 seconds. If you add JPA to the mix in a non-super trivial application, Quarkus native, it's still below, well, definitely below the 100 milliseconds. A bit more, of course, in JVM, because we're starting to start a lot of things here. And well, traditional clouds, they are beyond 9 seconds on this specific machine. Now, actually, these numbers are very conservative. Like, if you try it, I suspect you will see much better figures on your own machines. And so what's the developer joy I've been mentioning? In a nutshell, we have this comic on the website. You just change the code, and since it's very fast to restart the application, we just restart your whole server. Every time you refresh the browser, we restart it from scratch entirely. And okay, so the numbers I've shown before is like, so in JVM we can boot in about 2 seconds, but this is called boot start, right? If it's the same JVM and just needs to restart the entire application by dropping the class loader in there, then this is a warmed up JVM. We can restart your entire stack in milliseconds again. And that's not running GraalVM, that's running on HotSpot. Yeah? So that's fun because let me show you how an application in Quarkus looks like. So this is a demo. Well, I'm running a snapshot. I'm just showing you the POM file first. So we are importing a BOM from Quarkus, and then we import some of its extensions. So we will need Hibernate ORM, connection pooling, REST easy, and a driver to MariaDB. Now these are the Quarkus extensions. These are not forks of the original libraries, right? These depend on the vanilla library. They just add an additional thing, which is like the glue component between the rest of the build phases and the GraalVM compiler. So then we have a configuration file. It's a properties file in this case. We have some to configure a data source, which is a bit much. And then I'm telling Hibernate I want it to drop and create a database every time it's starting. And I also want to log all SQL statements. Now, in terms of classes, we only have 2 classes here. And that's the whole application. We have a fruit resource, which defines a REST endpoint on this fruits API. It's using injection of a standard JPA entity manager, and then it's using this entity manager to respond to the REST queries. And then we have a fruit entity, which is, again, a trivial entity, but it's showcasing, these are all like the standard annotations with standard features. So we have a name it query there. We're using a cache. And, there is an ID, there is a name. Very simple. So how does it look like? Let me start it. Maven package. So this is a normal Maven application. Nothing fancy here, except the fact that, oh yeah, I didn't show that. There is an additional plugin, which is the Quarkus plugin registered in the build, which is doing, yeah, I did it here. It was really fast. It's doing this augmentation phase, which is entire analysis of your code and enhancing of whatever needs to happen. Okay, so now we have built it. We can run it. Oops. Demo to runner jar, yeah? I start it like that, and it's up. It inserted cherry, apple, and banana in my database, and this is how the app looks like. So let me refresh. There are my 3 entities. I can, remove them, and I can enter something new. That's the full demo. Nothing fancy except that maybe the code is really simple in this case because the platform can handle a lot of this magic. But let's stop this and assume that we want to work on this. So we go in development mode. This is a special mode of Quarkus in which now, okay, it started. It also opened debugging ports and everything because it might be handy to connect to the JVM at any point. And it's up again. We can see there it is, and it logged some queries. So there are the 3 fruits again in the database. But now we can make changes to the code. And this isn't agent-based. Yeah? We're recompiling the entire application and restarting it from scratch, which means you have no limitations to what you can change in here. So let me say I go in the import SQL script here, and let me add a line in here. So I like mangoes. I save this, and then we go here and I refresh. I've seen that quickly there. It did something, and here we have mangoes now because it restarted everything. And you can make any change. You can make changes to the entity. Now, let me connect to the database. Here we have, show tables, show create table fruit. So this is how the table looks like now. We have a fruit table with an ID and a name. Now you can see the ID is an auto increment, and the name has a unique key on it. Now let's say we don't like the unique key. What do? You go here and you remove the unique key. Yeah. Now I need to refresh here to check. Okay, it's all done. I go back to my other terminal and check it here, and the restriction is gone. So you can totally have a lot of fun with Hibernate, like change the mapping or do anything. You just refresh and you see the effect. It can also fail, and it's fine. We can, I don't know, make an error here. I remove this and refresh. And oh, you have a compilation error in that line over there. No problem. You just go back and fix it. Oops, wrong shortcut. And you're up working again. No waste of time redeploying big applications or anything. Now, so we have apple, banana, cherry, and mango in this modified version. You can see here, apple is first, and then B, C, mango. Even though in my script, you see here, cherry is the one which has ID 1. That's because there is a named query on top here. Let me show it better, which is doing order by name. Now let's see, I want them ordered by ID, just for changing anything else. And now cherry is on top because we're sorting by ID. And that's development mode. I'm killing it because we need to speed up. I'm going to package it now, but as a native application. So this is fun. It's going to suck up about 10 gigabytes of memory from my poor laptop, which doesn't have as much, especially having the browser open and so on. GraalVM home not set. I'm not running with my variables set. Let's try again. Okay, so it's running tests there. Passed the tests. And Maven jar. It did the augmentation, and now we are in the native image phase in which here it's invoking that GraalVM specific command to compile an application. And now we see this is reporting here Hibernate core version, and I selected the MariaDB dialect and stuff, but this is compiling, right? In the compilation phase, it's starting our frameworks so that I have a chance to analyze what's going to happen at runtime, create all the metadata that's needed, and that's what's getting snapshotted and stored in the image as a pre-started executable. And well, this will take some minutes. Let me show you maybe, This is a dual core with hyper-threading, so it's being trashed right now. It's not the best lab machine to play these games. with 16 gigabyte of virtual memory used for this. I don't have 16 gig, so that's, oh no, it's not swapping. I probably have them, forgot. This will take about 3 minutes, so let me get back quickly to well, how it works. We said this, and we talked about this. So the principles are really that we are trying to do as much as possible during the compilation phase. And, well, you have seen that's not very slow at all, because we're doing that every time I was making a change and reloading the application. We do all of that work again, because you might have changed anything and we need to restart everything. Right? So that's very fast. And we're outputting generated bytecode, which contains like the constants and the snapshots of what has been generated during the build, or the output of the analysis that was run. So that same bytecode can then be compiled by the native image or can be run directly by the JVM. We generate a mix of static initializers and mains and, well, just general architecture here. The main components are the Graal SDK, so that we can feedback information to the Graal compiler about what's going to be needed. Gizmo is a new library that we're using to generate all this bytecode, which is representing the state. And Jandex is this library. It's giving us a full view, very fast and efficient of your application without initializing the classes, which gives us, the speed of rebuilding. And there are then extensions for any library you might want to use. Now, of course, we're working on a priorities base here, so we started with the cool ones or the ones we care about. If you need a library which is not supported today, actually the list on the project is much larger now in the project than what you see here, right? So check the master version first. There is a ton more stuff. For example, we just added Elasticsearch client and, well, a ton of other things. If something is missing and you need it, you can try ask us nicely. Maybe we can do it, or maybe I can help you or guide you into making that library compatible with GraalVM as well. Let's get back there. OK, build success. We have this running. So how do we run it now? There is a runner here. This doesn't have the jar, so I don't have to do Java -jar, and I just start it like that, right? Enter, and it's up. This started in 7 milliseconds time. And in that time, it created a connection pool. It connected to the database. It filled the connection pool. It actually created the schema, imported our fruits, started a transaction manager, and all the other stuff that you need, right? And we can have a look at how much memory that's using. Well, syntax error there. About 33 megabytes of total native memory, right? That's not heap. In practice, how much heap are we using here? I'm not sure, but we can try to limit it to 1 megabyte, just to have an idea. Yeah, it still works. It was a bit slower to boot, so 1 megabyte is a bit close to its limit. You see, it struggled a bit with the speed was much slower, but you're running in 1 megabyte heap size. Yeah? Now, of course, we don't want to run in 1 megabyte heap size. Let's be very generous and give it 5 megabytes. So it's whatever. OK. I have just 2 minutes left. So let me go quickly to, oh, this is actually it. Perfect time. So yeah, keep in mind the extension is doing several things. Like, it's not just making it compatible with GraalVM compiler. It's also speeding up the, it's giving you this hot reloading capability and making the whole framework much more efficient. So you can totally run it on a traditional JVM without drawbacks. So all the people who are a bit concerned about, oh, maybe the performance of GraalVM isn't, on par yet. Well, just run it on JVM, and it's great because it's using the same libraries you are already using in a different thing. It's just consuming way less memory. And yeah, you can have fun with the live reload. It's rebooting everything, so no waste of time there. We are on early days, so this is now 0.14. And which means, there are some issues which are open on GitHub. you can totally help. We don't have support for all the libraries which exist, but all the libraries we are building on are the stable ones. So, that aspect is stable. How we are composing the things, that's probably changing still, and that's all I had. Thank you very much. There are some pointers here for how to get started. And do I have time for questions? Yeah? Yeah?
What's the process memory usage between Quarkus with Graal versus just normal VM?
The process?
Yeah, of the actual process, because we've got all this native code. How much does it actually occupy the process?
Yeah, that's this RSS size that I was showing. So in this demo I just showed is 33 megabytes total process memory.
32 megabytes.
33, but yeah, approximately. Yeah.
If you have some libraries that aren't yet Quarkus friendly,
Yes.
can you still run Quarkus on the rest of the stuff and still run it in the JVM?
Of course, yeah. It's not breaking the JVM. The JVM is amazing and is working fine over there. And you can give it a shot in native as well, because the compiler is very thorough, of course, it's compiling it. So it's looking at everything, and if it sees something that it cannot compile, it will give you an error. Now, the error might be trivial to fix with some of the flags they give, or it might be more complex and then just run it on JVM. You can try. Yes?
Are there any plans to add extensions for server-side rendering, like file leaf or that kind of stuff?
Why not? Yeah, sure. I am not familiar with which libraries those might be. So open a ticket, and we can have a look.
Can anyone write one of these extensions, or does it have to be you?
No, anyone can. Actually, on the website, there is a guide to get you started into how to write an extension. Now, it is a bit complex at this point. We're hoping to improve both the guide and the API. It's a bit in early phases, but it's Apache licensed too, and it's on GitHub. Anybody is welcome to contribute. That's the whole idea. There are too many libraries that we can do. So if you need a library, please make an extension, and we're happy to help with that as well. Right? We probably cannot do them all, but we will help. Yeah.
Guessing you're not planning on working with Pivotal to get Spring compatible?
Well, why not, actually? There is an extension which supports the Spring dependency injection. So internally in the core, we have a notion of dependency injection. It doesn't have to be tied with specific annotations or specific standards. So you just need to have something that translates the meaning of that specific annotation, needs to generate this kind of metadata, and then the internal things takes it over. So actually, Red Hat Hero was a big fan of Spring Stack, contributed that thing because they said, I want to run Spring applications on Quarkus. And so he got started with that. So far, it only does handle the dependency injection things, but you could extend it and add more components to that. Yeah. Yes?
If there's a reasonable difference in the size of the native image versus the jar plus JVM, kind of size?
Well, I didn't explore that very much. So the difference is really the native image doesn't need the JDK, right? So you need to look at the JVM size and the native. But of course, the JDK can be modularized, so you can trim out the stuff that you don't need and maybe get close enough compromise. But that's going to be each scenario on its own different. Yeah. So I don't really know. Yeah?
What's the sort of size that you're looking at for a Docker image? Is that a native thing to just get it quickly into a Docker image?
Yes, actually the build tool has a flag to create a Docker image right away.
Is it optimized as well to go down to Alpine stuff, or is it?
I think that's being discussed. Somebody wants the Alpine, somebody wants to use just from scratch. We don't need any Linux distribution around it when you compile it as a natively, statically linked binary. So maybe you just need, nothing really.
But there's still the focus on optimization.
Yes,
cool.
Absolutely. Yeah. Sorry, it's first.
This metrics which you just showed, was it against the Graal Community Edition or was the
Community Edition? Yeah. You might get even better on Enterprise. We're not testing that, but it's the same. Yeah.
Do you came from? Like, what kind of code is most improved by?
Well, that's a very good question. The point here is two different compilers, right? So one is the C2 compiler, which does some amazing things. Then there is the GraalVM compiler, which does some other amazing things. So it will depend what code exactly is getting optimized better by one or the other. And we don't really know much. What I know is the GraalVM compiler is much better at dodging object allocations. So if you're limited by like memory usage or GC, that one would be better.
I guess my question is more on the, not even the GraalVM, but just Quarkus, OpenJDK versus others.
Other
The other 2.5 to 9.5 seconds.
Oh, other frameworks you mean? Still compiled by the same JVM.
That 2.5 to 9.5 second differential that you showed, where was the
Okay.
saving?
Yeah, well, lots of things. Like, yes? What, last one? Okay,
Yeah.
okay, yeah. So one is class path scanning, right? We know everything in one single shot because all the frameworks register what they are looking for into the indexer, and then the indexer does a single pass on behalf of any amount of frameworks you have. And it's the same as for bytecode enhancement and manipulation. Like your classes are being enhanced in one shot on behalf of all the frameworks on top of them. So if you have REST-easy needing to do something, dependency injection needing to do something else, these things are not done by different phases of optimization on the same bytecode. It's one single visitor phase. So you get a lot of build time optimizations there too. Thanks very much.